Welcome to Electrical Engineering with Excel. In this video, we will take the spreadsheet we made for semiconductor thermal calculations a step further. Instead of manual inputs for the heatsink and the thermal interface material resistances, we will make a drop-down list selector that calculates or selects the resistances from tables. It uses the powerful features of Excel tables. Recall from the Digitizing Spec Plots video, we digitized a heatsink specification plot like this. You would normally draw a line up from the power dissipation axis to the curve and read off the temperature rise from the y-axis, then divide the temp rise by the dissipation. We used a plot digitizer and put the XY pairs it generated into Excel and let it create a trend line. In this case, the natural convection curve aligned with a third-order polynomial. We put those coefficients in a table and calculated the thermal resistance from the polynomial. We will exploit that same construct here. We will also include the data for the heatsink when forced air cooling is used. In most cases, the relationship between the dissipated power and the temperature rise is very linear with forced air. Look how close these straight dashed lines lay over the top of the graph. For the case of the 200 linear feet per minute and 10 watts, the table shows a temp rise of 54.09 degrees C. That matches the graph here. To get the temp rise per watt, we can divide by 10 and use 5.409. Notice the table value for 1 watt is slightly less than the 10 watt value divided by 10. That makes for a small amount of built-in conservatism. Being linear, we can use the same polynomial formula we use for natural convection, but only use the C coefficients. With A, B, and D being 0, the delta T is simply C times the power. We will make strong use of Excel tables using data validation and XLOOKUP functions to make a drop-down material selector for our design. We will begin with a brief overview of Excel tables. When data is converted to an Excel table, the data in the table has what's called structured references. It's like having assigned range names for the cells, datasets, and headers. I've selected a single cell in the D column here. I typed in an equals sign in cell F4 to display the structured reference. It has the table name Heatsinks, followed by the @ sign and the column header D, enclosed in square brackets. The @ sign means it's relative to that selected row. If the header has spaces, the header text is enclosed inside another set of square brackets. Here's the entire data set of column D selected. Now the structured reference is just D without the @ sign. Next, just the column header is selected. Pound headers is in brackets, followed by a comma, and then the column header D in another set of square brackets. Now the entire data sheet is selected and the structured reference is simply heatsinks. With the entire table selected, including the header row, the reference is heatsink with pound all in the brackets. Let's go to the spreadsheet and get started. I have some data with a header row that we will return into a table. Click anywhere in the data set. You can select Format as Table from the Home tab, or from the Insert tab, select Table, or use shortcut key Control-T. Excel recognizes the range of the data and that it has headers. Press OK. We just created a table. With any cell in the table selected, the Table Design tab appears. This allows you to turn off the header row or filter buttons and more. You can select banded rows or columns or not. I'm going to write the temp rise polynomial formula in an adjacent cell to the right. Not only does the table automatically expand to another column, it also spills the formulas down the column. I'll now add the thermal resistance formula, the temp rise divided by the power dissipation. Entering new data is a breeze. Notice the table expands when I enter data in an adjacent row below. I'll copy the coefficients down to the new row. Any formulas or formatting will be applied to the new row content. To select an entire column, hover over the top of the header row until you see a 4-arrow symbol. You can drag the column to another location. You can do the same with rows. Hovering just slightly below the top of the header row shows a single down arrow. Clicking there will select the data set. Let's say you add a new row by mistake that expanded the table. You can grab the table content handle on the bottom right and move it up to compress the table. In the thermal calculator spreadsheet, we manually entered in the thermal resistances. We will now look up the coefficients from the table. From the Insert tab, select Table. It recognizes the header row. We will name the table Heatsinks. Going back to the thermal device calculator, we will put in a drop-down list. From the Data tab, select Data Validation. Select the Allow criteria to be a list. Then go select the Description dataset. Now we have a nice drop-down list of heatsink descriptions. Let's add a new heatsink row. Although the table expanded, the list doesn't have the new item. Let's go get the structured reference for the description column. Just type = and select the data set. Then go up to the formula bar and copy the structured reference. Now let's go back to the data validation and paste it in. We get an error. Data validation does not accept table structured references. But what you can do is use the INDIRECT function. We just need to put the structured reference inside quotations. Adding a new item now shows up in the list. Now let's write the polynomial formula for the delta T and calculate the selected heatsink's thermal resistance. First, name the selector cell as Heatsink Select. To make it easier to write and interpret the long formula, let's expand the formula bar to show multiple rows. Using the XLOOKUP function, the lookup value is the selector cell content. The lookup array is the description dataset from the table, and the return array is the A coefficient dataset. Now multiply the coefficient by the power dissipation cubed. Now copy that whole line and press Alt-Enter to create a new line. Add the plus operator and paste the content. Do this 2 more times for all 4 coefficients. I forgot a plus sign here. Now for the coefficient B, change the exponent to squared. Do the C coefficient and remove the exponent. And then for D, remove the dissipation. Now that's the temp rise. Put parentheses around the whole thing, and then divide by P_dis. Now we have the thermal resistance of the selected heatsink. Notice it's showing an error flag. It detects the formula inconsistent with the ones around it because it is not locked. We can fix that by changing its cell style to outputs. We need to make the selector cell the input style so it is selectable when the sheet is protected. We will need the device thermal areas. In the thermal calculations video, I showed where I had an outline area of the TO3 case. I thought it would be nice to make the lead hole diameter an input, since some heat sinks adapt for larger diameter pins. Calculate the screw hole area using pi r squared. And the same for the lead hole. Then the total surface area is the outline area minus the screw hole area times 2 minus the lead hole area times 2. Let's do a similar thing for the TO220 package. I pasted in a drawing with a dimension. The thermal tab area is calculated from those drawing dimensions. Calculate the screw hole area with pi r squared. I wanted to make a selector to include the screw as a thermal conductor or not. Select Data Validation and select List. In the source box, just type in a Y and an N separated by a comma. Set the cell style to inputs. We will calculate the thermal surface area with an if statement. If the TO220 screw select is no, the area is just the tab area minus the screw area. Otherwise, it's just the tab area. Now we will make a table for the thermal interface materials. Thermal resistance will be calculated based on either conductivity or bulk resistance. We will make it smart to know which one. Make it a table and turn off the filter button. This is a TO220 pad, so we will need to set the area to the TO220 total area value. Now we need to convert the area using the convert function. The from unit is square inches and the to unit is square meters. Also convert the length from inches to meters. Calculate the resistance per the equation above, which is L over K times A. We must prevent data from being entered on both the conductivity column and the bulk resistance column on any given row. This can be done with data validation. Select Custom from the criteria, then use the isBlank function with the argument as the conductivity cell H5. Make an error alert titled Unallowed with the error message saying properties K or R is a single allowed entry, not both. Entering a resistance here gives us the unallowed message. Now let's do the same for the conductivity cell data validation, the isBlank function with the cell I5. Entering resistance here when entering conductivity gives an error, but we need to set the same custom error alert as before. Adding another material that has bulk resistance for the thermal resistance calculation, we will use an if statement based on the bulk resistance cell being blank. If true, calculate the previous L over Ka. If that is false, it returns the bulk resistance over the area in square inches. I'm pasting in a variety of materials. Notice the bottom three are for TO3 cases. We need to go change the area reference to the TO3 total area value and copy it down. Notice an error flag. It knows the formula is inconsistent with the other formulas in the same column. We will just select Ignore Error for these, although it's not necessary. From the Table Design tab, we will name the table Insulator Pads. Type in the equal sign and select the description dataset to get its structured reference. Then copy it from the formula bar and delete the data displayed in the sheet. Now let's make a drop-down selector and name it Pad Select. As with the Heatsink selector, do data validation, select List, and use the INDIRECT function using the quoted structured reference. Make that an input style. Now for the thermal resistance cell, we can use XLOOKUP with the selector cell as the lookup value. The lookup array is the description dataset, and the return array is the thermal resistance dataset. We are getting the error again about the formula not being locked. That can be fixed by making it cell style outputs. I'll put some headers above the drop-down boxes to make it more obvious that it's a user input selection. I'll also make the text a little bit smaller so more of the description is readable, consistent with the text displayed in the drop-down. Now let's put it to use. Selecting the smallest TO220 heatsink makes the junction temperature go red, being above the 120 degree D-rated value. Selecting the next larger heatsink brings the junction temperature down to 115.6 degrees C. I thought it would be nice to add some hyperlinks to datasheets on the manufacturer's websites. I find it easier to copy the link address than from the Insert tab select link. It shows up as a recent item and can be selected there. Now I'll just rearrange things. Now let's protect the sheet and see how it reacts. I'm trying to delete these output and reference cells. And of course, the yellow input cells can be changed. It's a nice feature to keep users from messing up the formulas. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.